17 August 2017, 8:41 a.m. Eastern Daylight Time. The world prepares for a solar eclipse. Many Americans are making their way to the path of totality. But unknown to most, the universe is, at this moment, delivering a light show of far greater power and significance. "130 million light years out, in a galaxy astronomers call NGC 4993, two ancient and powerful stars are climaxing a dance that began 11 billion years earlier. Their fateful embrace has torn the partners to shreds, but has given rise to something new. And for the first time, astronomers are able to both see its light and hear its gravitational thunder. On that August day in 2017, a new type of laboratory records what scientists describe as a ripple in the fabric of space-time. The lab is actually a pair of L-shaped detectors, each leg 4 kilometers long. But they're separated across a continent. Together, they're called the Laser Interferometer Gravitational Wave Observatory, or LIGO. And the signal this lab has caught is different from, and much longer than, any they've seen before. Less than 2 seconds later, NASA's orbiting Fermi Gamma Ray Burst Monitor notes a weak spray of high-energy photons. The European Integral Space Telescope has seen it too. The European Virgo, a close cousin of LIGO, hasn't detected anything. But the instrument has known blind spots, which actually narrows down the search to an area in the Hydra constellation with about 50 galaxies. Urgent emails go out to observatories across the world. Hunt for the afterglow. Wide-field telescopes begin looking for anything that wasn't there before. Atop a mountain in Chile, the relatively small 1-meter Henrietta Swope telescope takes a telltale picture in NGC 4993. It's an old galaxy. Most of its big stars have long since exploded, leaving behind black holes and neutron stars. Chat messages fly across the world between research centers. In just 45 minutes of comparisons to earlier images, astronomers pinpoint a bright new object. Other telescopes confirm it. It's the violent merger of 2 super-dense neutron stars. As they spin closer together, the pair bleeds orbital energy into gravitational waves. They crash with a flash of gamma rays, touching off a bright outburst that astrophysicists call a kilonova. For the first time, a single astronomical event has been both seen and heard to most people, the world is a colorful place. But we actually see only a tiny sliver of all the light around us. Specially designed telescopes can see cosmic events in other wavelengths of the electromagnetic spectrum. And new gravitational wave interferometers, the twin LIGO facilities in the US and the Virgo instrument in Italy, can go beyond. Each of the three compares the changing length of a laser beam as a passing gravitational wave warps our planet. Their extremely sensitive mirror systems can recognize ruffles in space-time, disturbances from violent events long ago and far away. Electromagnetism gives astronomers the sight. Gravitational waves now offer them the sound. LIGO and Virgo have previously spotted several mergers of two black holes by their characteristic short chirps. But the new detection plays out over more than a minute, nearly 100 seconds. That indicates the collision is between two objects, still heavy, but lighter than black holes. Neutron stars. When neutron stars smash together, magnetic fields 1 billion times stronger than our sun's swirl around the crash site, quickly organizing themselves into polar jets that stimulate the gamma ray burst. Newly liberated subatomic particles bombard the shredding star layers, making new, heavy elements and blasting them into interstellar space. In NGC 4993, all of this happened 130 million years ago. Here on Earth, the first flowering plants were just blossoming, and the newly evolving birds had only recently split from dinosaurs. As the light from the kilonova finally reaches Earth, the Hubble Space Telescope watches the glow. At least 70 different ground-based telescopes make more than 100 observations in the visible and infrared. More than a week after the signal first hit LIGO, the orbiting Chandra X-ray Observatory spots a blush of X-rays at the same location on the sky. This 8-day delay tells astrophysicists this merger produced very tight jets of particles not pointed at Earth. And that explains why the Fermi satellite gamma ray data were unexpectedly faint. In just a few weeks, this faraway marriage of neutron stars has been observed in every part of the electromagnetic spectrum and with gravitational waves. When a single event is observed at diverse wavelengths with different types of instruments, scientists call it a multi-messenger detection. Seeing this first kilonova proved that gravitational waves travel at the same speed as light. And if you look at the spectrum of that light, you can see what the component stars were made of and what they made as they exploded. The gold in our jewelry, the uranium in our power plants, the rare earth elements in our electronics, all were created within exploding or colliding stars. Neutron star crashes billions of years ago made it possible for us to build spacecraft and advanced telescopes. As a star at least 8 times more, but less than 30 times more massive than our Sun, reaches the end of its life, it collapses, triggering a supernova explosion. When the celestial smoke clears, what's left behind is a rapidly spinning, ultra-dense core. It's only 10 to 20 kilometers across, but it weighs more than our Sun. As it rotates, it may fire off tight particle beams at nearly the speed of light. If we see them rhythmically sweeping across our line of sight, we call it a pulsar. Neutron stars are often found in binary pairs. As they orbit closer and closer around their common center of mass, the revolutions grow faster and faster. At the moment they join, a short burst of gamma rays and a lasting X-ray afterglow confirm the new creation. The end result may be a black hole, or it may be another long-lived or short-lived neutron star. And of this first detection, astrophysicists don't yet know which. The laser interferometers that kicked off this rapid chain reaction of scientific discovery are themselves triumphs of science and engineering. Albert Einstein, whose 1915 general theory of relativity predicted gravitational waves, believed such instruments could never be built. Their development, a century later, earned their builders the 2017 Nobel Prize in Physics. The two LIGOs and the Virgo are not directional detectors, but combining their data sets can begin to roughly suggest the source location on the sky. Getting matching visual signatures at many wavelengths takes a lot of dissimilar telescopes closely cooperating and coordinating. This kind of science is much bigger than any one institution or nation. Next, international multi-messenger astronomers will be looking into their data streams to find the sights and sounds of a neutron star merging with a black hole. Astronomers need to know how often the different types of stellar smash-ups happen and what is left behind when they do. Because those answers can tell us where all the elements in the universe came from, how large the universe actually is, and how fast it is expanding.